Going to start with pulmonary ventilation. Okay, so we're looking specifically, when we're talking about the air coming in, air going out, we're not really talking about respiration. We're going to talk about breathing, mechanics of breathing a little bit later on. Respiration is what happens at a cellular level, right? Cellular respiration. Breathing is the mechanics of bringing in the air and blowing off the CO2. So to start off, we're going to begin with some standard notations. These are things that you are going to need to know, and you should know the difference between the lowercase and the uppercase letters for A specifically. A lowercase a is for arterial blood. If it's a capital A, it means alveolar gas. So anytime we do any of these symbols, the P of whatever X is, that's going to be your partial pressure. The F is going to be the fractional volume or pressure, the fraction of that resides in air. How much, what would be the fractional value for oxygen in the air we breathe? About 21%-ish, right? So it would be 0.21. So that would be the fraction of oxygen in the air you breathe. About 78% roughly for nitrogen. So, but as a decimal, 0.78 for nitrogen, 0.21 for oxygen. We'll get to these a little bit later. 0.03 for carbon dioxide. S of X will be the saturation. That'll give you the percentage of hemoglobin that's saturated, which is going to come up a little later. C, usually in the figures that come from the boron book, this is, I think, this is a table that is actually shown, I believe, in the boron book. If it's a C of X instead of having the brackets around it, sometimes that's how they denote concentration. So I want to make sure you understand what that specifically is. Lowercase a, b, and c, that's your arterial blood, your mixed venous blood, and your pulmonary capillary blood. And then the capital A, I, and E are going to be your alveolar gas, inspired gas, and mixed expired gas. So all of these are going to be used pretty much in every single lecture that we talk about, so it's going to be important that you remember what these mean. Yeah.
So, like in the examples, are you going to make it pretty obvious that you're talking about the total oxygen content and not just carbon dioxide, since it's CO2 and CO2?
Oh yeah, no, so if I'm going to, on like an exam, I will make sure that if I do C of O2, it'll be subscript O2 instead of CO2 together. But most likely I would probably put it in brackets because I think that is more logical. But I wanted you guys to know that this is how I think the boron book is going to do their abbreviation, and a lot of our figures are going to come from the boron book for the respiratory unit. So I wanted to say that up front. So if you don't see brackets and you're wondering what, you're right, CO2 is, it's not carbon dioxide in this content. It should show up as a subscript of O2. So it would be the content of oxygen. And I'll say that and point that out when we start talking about this. But that's a good point. That's a good question. All right. So first off, we have a review of our gas laws. We're going to cover Boyle's law, Charles, Dalton's, and Henry's. We don't really spend a little bit of time on each one of these, but it is important to understand how all of these are going to work together, specifically because it's going to come into play when we start talking about how the respiratory system functions at different air pressures, when you're high altitude, when you're under water, and just at various levels above or below sea level. So Boyle's law is basically looking at the relationship between pressure and volume. In a closed system, if your volume increases, what happens to your pressure? It decreases, right? Bigger volume, lower pressure. Assuming that everything else, your temperature stays the same, the number of moles of gas stays the same, and it's in a closed system. If you increase the volume of that gas in that system, the pressure is going to drop. So the pressure and the volume are actually inversely related. And if you rearrange this equation, you would have P1 over P2 equals V2 over V1. Okay, so inversely related for pressure and volume. Charles' law looks specifically at the temperature. What happens to your volume as your temperature goes up? Again, in a closed system, assuming no change in moles, assuming that the pressure is still constant, what would you see happen in a closed system of a unit of gas if you increase the temperature? It's going to increase, right? Volume's going to increase because you're basically increasing your kinetic energy, and that's going to cause the molecules to spread further apart. So Boyle's law, we have an inverse relationship between the pressure and volume in a closed system. Charles' law, we have a direct relationship between volume and temperature in that closed system. Dalton's law simply says that if you're looking at the total pressure of a gas, you can add up all the partial pressures of the individual components of that gas. So barometric pressure will add up the partial pressure of oxygen and nitrogen and carbon dioxide and water vapor. Okay, that's going to be really important specifically for understanding how these gases are going to function. They're not chemically interacting with each other. They function independently when they are in a gaseous solution. Okay, so Dalton's law says that you can add up the concentration or the partial pressure of every single one of these gases. Henry's law specifically looks at the concentration or the content that's of a dissolved gas inside of a liquid. That's going to be the solubility of that gas in that liquid times the partial pressure of that gas. So if you elevate the partial pressure, what are you going to do to the amount of gas that's going to be dissolved? You're going to increase it, right? It's a direct relationship, okay? That solubility is for that particular air-water interface is going to be constant. How likely is it for that particular gas to be able to dissolve in that particular fluid? That's going to be a constant for a given air-water interface. Okay, so these are ones that we are going to need to know. They all really stem from the universal gas constant. So, what is P? Pressure, V, volume, N, number of moles of the gas, R, universal gas constant, and T is temperature in Kelvin. Okay, so this is basically showing you how all of these are going to relate. Assuming the same number of moles, and obviously the gas constant will be a constant. The bottom is showing you what it would look like during inspiration, which for the pulmonary unit is going to be inhaling, okay? Inspiration is how you refer to breathing in, expiration is breathing out. So on the left we have the diaphragm contracting. When the diaphragm contracts, what happens? It increases the volume of the thoracic cavity. When you increase the volume of the thoracic cavity, the pressure is going to go down, okay? That creates a pressure gradient for air to enter the lungs. When the diaphragm relaxes, it comes back up. So whatever volume is in there, it's going to decrease the overall volume and therefore increase the pressure. Now you're creating a reverse pressure gradient so that it's going to flow out passively from high pressure inside the alveoli to low pressure outside of your mouth. We're going to repeat all of this stuff. This is just a quick introduction to it. We're going to get to the mechanics of breathing and we'll talk a lot more about this. All right, so we just went through, and I apologize. My intention here was to write the that it's degrees Kelvin, but you know you don't actually put in degree, so cross that off on both of those. So this is really just a summary of what we had talked about, but first thing I want to introduce is we're looking at Boyle's law. We have an inverse relationship, as we said, between volume and pressure. This is going to be at the crux of your mechanics of breathing. How is it that we decide which direction air is going to flow? It's always going to flow from high pressure to low pressure, okay? That is what drives air entering into the alveoli and air leaving the alveoli. It's also going to be important when we talk about adequate distribution of air within the various alveoli. Not every single alveolus is going to get the same amount of air. So, assuming same number of moles, assuming constant temperature, higher volume, lower pressure, lower volumes, higher pressure. So, each, for Dalton's law, so that was just a review of our Boyle. Dalton's law, we had already introduced this. Just to kind of walk you guys through it again, each gas is going to behave completely independently when they're in the air that you're breathing in. Okay, so just because you have nitrogen and oxygen floating around in the air doesn't mean you're going to spontaneously start breathing in nitrous oxide. Okay? That's a good So you can add up all of the partial pressures in order to account for the entire barometric pressure. So if you have a list of partial pressures and you're looking for barometric pressure, and I ask you for one that you don't know the partial pressure of, how are you going to figure it out? Simple subtraction. Okay, you're going to add everything else up, subtract it from barometric, you can get the partial pressure of that particular molecule. Okay, now, one of the most important things to remember is that we do breathe humidified air. Even if the air you're physically breathing is completely dry, 0% humidity, the air that gets into your lungs is humidified. Your nose, your upper airway passages, the conducting airways are going to add water vapor to the air you breathe. So anytime we talk about the partial pressure of oxygen or carbon dioxide, specifically in the alveoli, you're going to have to figure that out by handling and making an adjustment for the fact that you've added humidity to that air. Okay? This is also why sometimes you tend to be very thirsty in the morning. You lose a lot of water vapor just by breathing overnight. So, no matter what the air is like that you're breathing, it's always going to be humidified by the time it gets down to your lungs. So, looking here, this figure is also, again, from the boron book. We have a dry air phase. We also have what's called a wet air phase. This wet air phase is really your unstirred layer. It's an unstirred layer right above the water that tends to be a little bit more humid than the air above it. So if you were to look at the partial pressure of oxygen at the top, since it's 21% of sea level, in this case 1 atmosphere or 760 millimeters of mercury, you will get a partial pressure of about 159, 160. Because we're looking specifically at humidified air, you have to take into account that you've added this water vapor to the air that you breathe. At 37 degrees Celsius, so body temperature, that is going to be a magic number of 47. That 47 is something for you to remember. Okay? It's going to make it easier than trying to calculate what that partial pressure is going to be. But anytime we're talking about humidified air that you're going to be breathing, you always need to take into account that 47 degrees. Will it be a little bit different if you have fever? Yeah. But for all intents and purposes, that is going to be the number that you're going to use anytime you need to account for water vapor in the partial pressure of the air you're breathing. So, to look specifically at the fraction of dry air. There we go. Okay. So, the fraction of dry air is the same as what we always said. Oxygen is going to be about 21% of the air that you're breathing. That's just the way it is here on Earth. In order to figure out what the partial pressure is of the air that you're breathing, as opposed to the partial pressure of air in the dry air around you, you need to take whatever the barometric pressure is. So a lot of the ones that we're going to be doing are going to have you at sea level, just for ease of calculation. 760 minus that 47, because of the humidity that you're adding in as you're breathing in. The end result is that you get 149. You lose about 10 millimeters of mercury that is oxygen inside of your lungs. So it will be lower than the partial pressure of oxygen in the air that you're breathing if that air is completely dry. Okay? So this kind of combines your Dalton's law, and it will take into account our Henry's law in just a little bit, because when we start talking about the gases that we are breathing in, eventually where's that gas going to go? Where's your oxygen going to go and your carbon dioxide coming from? How does it get to the rest of your body? Blood. Okay, so we're going to have it entering your liver. So Henry's law is going to come into play when we start talking about how that gas is getting in and out of that liver. Does anybody have any questions about this so far?
Can you explain 47 here?
The 47 is if you were to calculate the partial pressure of water vapor in humidified air at our body temperature. So specifically at that 37 degrees Celsius. So using the normal universal gas laws, you could calculate that value. We could run through that if you want to after class, but the value that it comes out to at body temperature is 47 millimeters of mercury. So anytime we're talking about air inside your lungs, you always need to take that into account. Okay, so you'll get barometric pressure, and then I'll say, what's the partial pressure of oxygen or carbon dioxide inside your lungs? You'll need to make sure that you don't forget to subtract that. Yeah.
So the 149, that's in the lungs.
Yeah. Sorry. Yeah, the figure of the beaker was just to show the air-water interface, but it's specifically looking at the water vapor in the lungs. That's not too far off from the water vapor that you would have in the air if you had humidified air at the same. Okay. All right, let's see if I can zoom in a little bit because it's kind of small. But if I try to enlarge it, it made it look kind of funny. All right, so this is the exact same calculation if you were specifically looking at the partial pressure of carbon dioxide. The fraction of carbon dioxide in the air is 0.03%. Again, if you're looking at the carbon dioxide that's going to be inside of your lungs, humidified air, any type of humidified air, you have to take into account that 47 degrees. And there's that, in case you didn't see that, it's on the bottom of that 37 degrees, so you know that all of this is in reference to body temperature. Okay? How is that far? We're kind of easing into it. It's going to get more fun. All right. Somebody had a question? Yes.
Okay, so the barometric pressure is all of the partial pressures added up together, right?
Yes. Yeah. Assuming that you don't forget to include any of them. Yeah. Okay. So on the left-hand side, we're looking at the dry air, atmospheric. So this is really just to compare what you would see for the the specific partial pressures that you would see for the fraction of dry air and the partial pressure that you would see at sea level for each one of the typical gases that you would find in atmospheric air. If you look at the wet air in the trachea, you'll notice that the fraction of that air is a little bit lower. Why? What do we have to take into account now? You have to take into account the water. That's the big difference between these two. In dry air, the fraction is 0. In wet air, you actually have to take into account this fraction of water vapor. That's why the rest of your fractions are going to be different than what you would see at dry air. So you could still, if you wanted to, memorize all of the fractions for dry air and all of the fractions for wet air. Or you can take the barometric pressure of dry air and subtract the 47. I think it's easier to remember one number rather than like 5. So you could take whatever the total pressure is inside of your lungs and multiply it by 6.18 for that percentage, for the fraction, and get the value of 47 at your body temperature. That's where that value comes from. So if you wanted to, you can figure it out that way. You think that would be easier? I think it would be easier to remember the one number, 47. It's pretty much mostly going to give you information about calculating at body temperature. All right. So, Henry's law. Henry's law specifically is going to look at how likely is it for a gas to be dissolved in your blood. Because we are going to have our oxygen and carbon dioxide inside of our blood in a couple different forms. One of those forms is going to be how much of it is actually being dissolved, okay? So on the left side, both of these are going to be at 37 degrees. Your first solution you see above in the partial pressure of oxygen in the air surrounding that beaker is 100 millimeters mercury. That's higher than what you see in solution 2. What do you notice about the content of dissolved oxygen in each of those beakers? Which one's higher? The one that has the higher partial pressure of oxygen above it, okay? And that goes back to the equation that I mentioned before, where you're looking at the actual content of gas dissolved in a liquid is going to be the solubility of that gas at that particular air-water interface, or air-liquid interface. It's going to be water for our lungs, but just for all intents and purposes, this is a universal law that will apply to air-liquid interfaces. So at that gas-liquid interface, that solubility will be multiplied by the partial pressure. So if you elevate the partial pressure, you can get more of that gas dissolved in that liquid. Okay? And I believe, yes, there is a little demonstration that shows you how that works, specifically looking at regular distilled or, non-carbonated water compared to carbonated water. And it's going to use a pH indicator to show you what happens to the level of acidity of the water during the course of this little experiment that they do.
1, 2, 3, up!
Sorry. I always forget how loud it is. It's important for those of you that have done lab work before to remember that this was not phenol red, this was methyl red, which means that the red is going to show you an acid and the yellow is going to show you a base. So anybody that did micro, you might have noticed that it seems to be the opposite from the base acid. So in this case, if you have a yellow color for this pH indicator, the pH has gone up. What happened when they basically created a vacuum? What did they do? They lower the pressure, right? And if they lower the pressure, what does that mean for the amount of CO2 that was dissolved in that soda? It went down, it came out of solution. As it came out of solution, it created a pH that was actually elevated compared to original. Okay, because when you have carbon dioxide dissolved in a liquid, more carbon dioxide means a more acidic solution. Okay, so this was a way to provide sort of a visual representation. What happens if we change the pressure right above a particular liquid and dealing with the gas that was present in your soda? It can show you how you can decrease the amount that's dissolved and increase the amount that's dissolved. As soon as they returned the plunger back down and elevated the pressure of that air-water interface, what happened? That CO2 went back into solution and the pH dropped. Okay? How do we feel about that? Okay. All right, so Henry's law, specifically we talked already about pressure and solubility. It's also important to note that we do have a relationship between temperature and solubility. So the classic example would be to take any kind of carbonated beverage, which is under pressure. When you open it up, what's the first thing you hear? Right? You're releasing that pressure, so a lot of that gas that is dissolved in your carbonated beverage is going to come out as solution. What happens if you have a open container of a soda in the fridge versus a soda on the counter? Which one's going to go flat faster? On the counter, right? The higher the temperature, the lower the solubility. The lower the temperature, the higher the solubility of that gas in that liquid. So if you don't want flat drinks, you refrigerate. Okay, quick question for you guys. Based on what we talked about already for Henry's law for gas solubility in a liquid, how do you think that might explain the benefits in that? Okay. So one of the main consistencies that I'm seeing is that when you go deeper underwater, pressure is going to increase. If you want your lungs still to inflate, you have to increase the pressure of the air that you're breathing. Because the pressure that is being exerted on your body has increased. You still need to be able to counteract that in order to open up your lungs and allow air to come in, okay? So the pressure of the air that you're breathing when you're scuba diving is going to be higher than the pressure you would breathe at the surface to counteract or basically balance out the pressure of the crushing water that is engulfing your body. If you increase the pressure of the air that you're breathing, what does that do to solubility? It increases it, right? Higher pressure means the higher partial pressure, because your partial pressure of any particular gas is just the fraction times that barometric pressure minus your water. So if you elevate the pressure of the gas that you're breathing, you're going to increase the solubility of that gas in your blood. Which gas is going to cause the problem? Nitrogen. Nitrogen is the one that's actually causing your problem because it's inert. It's not something that your body normally utilizes. It's not taken up by the cells to be used as, a source for respiration. It's an inert gas that it just makes up 78% of the air that you're breathing. So, if you are increasing the pressure of the air that you're breathing, you're going to end up with more gas dissolved in your blood. Since it can't bind to hemoglobin, all of that nitrogen is going to be in the plasma portion or the liquid portion of your blood. Okay? What happens if you surface too quickly? What happens to the pressure of the air that you are breathing? What happens if something happens while you're underwater and you surface really fast? What's the pressure on the surface? Higher or lower? Lower. It's going to be a lot lower. Okay? What happens when you start breathing air that is lower pressure? What's going to happen to all of the pressure and all that dissolved gas? It's going to come out of solution. Okay? That lower pressure is going to result in that particular gas, in this case nitrogen, coming out of solution. You can get what's called an aeroembolism, which is sort of like an air bubble clot, for lack of a better word. Okay? Those aeroembolisms are going to cause a lot of pain. They can cause a lot of other issues, but most of the pain is usually from it showing up in like your synovial joints. But it's because of Henry's law that you would see something like this happening. It's also the same reason why you can't dive in colder water for as long as you can in warmer water. Okay? Because colder water is going to do what to solubility? Increase it. Okay? So when we're talking about Henry's law, pressure that's high and temperature that's low are both going to elevate the amount of gas that's able to dissolve in your blood. Okay, and if you have a sudden drop in pressure of the air that you're breathing and the pressure of the body around you, that gas can come out of solution more quickly than your body's able to handle. It's also the reason why you don't dive and fly in the same day, because you're going from very high pressure under the water to very low pressure up in the air. Even though they pressurize your cabin, it's still not the same as being at sea level. Okay, any questions on that? Okay. All right. You have two different pathways by way your oxygen and carbon dioxide get to your body. You have convective pathways and you have diffusive pathways. Your convection is either going to be through airways where there's no gas exchange, or it's going to be through your blood vessels, again, where there's no gas exchange. So we're looking at the circulatory system on the bottom. That's your internal convection. Your external convection is the air that you're breathing in as it passes through the upper bronchi and upper bronchioles, well, upper bronchi of your airways. So through your trachea, the upper bronchi, before you start to get to any alveoli where you can have gas exchange occur. That's convection. That just means that you're going to send those gases to and from the body without any real exchange across the barrier of that airway or across the barrier of that blood vessel. Diffusion occurs at 2 points. It occurs in your lungs, mainly because your alveoli are very, very thin. The membrane is very, very thin, so it's easy for gas to pass across the alveolar membrane into the capillary beds, and then you get diffusion again occurring once you get to the systemic capillary beds as well, between the tissues and then the blood vessels that are serving those tissues. So 2 different ways, convective movement and diffusive movement. Okay? It's going to be for both the pulmonary and your blood circulation that you're going to have one part that's convection and one part that's diffusion. Now, in order to determine at what point you start to see that diffusion, has a lot to do specifically with the appearance of your alveoli. For generations 0 all the way down to 16, there are no alveoli. This is your convective movement. These are what's called your conducting airways. They are not going to allow any gas exchange because there's no alveolus anywhere in there. When we talk about generations, we're talking about going from one trachea, branching out into large bronchi and then into smaller bronchi, just like we saw with hemodynamics and the circulatory system. Every time you have a branch, that's a new generation. Okay? So, generation starting at the trachea at 0 all the way down to 16, no gas exchange. Why? No alveoli. You don't get gas exchange until you see alveoli. Alveoli are going to start showing up when you get here. So at point 17 is where you start to see alveoli showing up on your respiratory bronchioles. Your terminal bronchiole is the last conducting bronchiole. Bronchiole is similar in terms of size to arterial, right? You went from aorta to arteries to arterioles and down to capillaries. In this case, you go from trachea to bronchi to bronchioles down to alveolar ducts and alveolar sacs. Once you're past level 20, so to speak, you get down to those alveolar ducts and those alveolar sacs. These are the points where you're going to have gas exchange occurring, and most of your gas exchange is going to occur when you get down to those alveolar sacs. You see a progressive increase in the number of alveoli from generation 17 all the way down to 26. One point that I do want to point out in here is this guy. The pores of Kohn. Sounds like a very nice little name. So right there. These pores actually reside between neighboring alveoli, and they can serve a function to help prevent lung collapse or alveolar collapse. One of the things they can do is sort of provide a collateral movement of air to help balance out the air that is entering into these neighboring alveoli, so that some of your smaller alveoli are not going to tend to collapse. Okay? But they do reside to connect all of your neighboring alveoli as a way to protect against uneven ventilation and therefore collapse of ones that are not being ventilated. Okay. Any questions on this? All right, so specifically looking at the movement of air. One of the things that's important to pay attention to is that the velocity of airflow is going to be related to the flow that is happening over the area, the cross-sectional area of all of those airways. So in this case, you're looking on the x-axis that has your airway generation number. So your conducting airways you see in the red, it ends with that dashed line at level 16. Once you get above that blue area from 16 up to 20, until you get down to the alveolar ducts and sacs, that's your alveolar airways, your alveolar bronchioles that actually can participate in gas exchange. As you move from airway generation number increasing, you're going to see that the cross-sectional area is going to increase. The velocity of flow, the air velocity, is going to drop. So you have an inverse relationship. Now, who notices something weird about this one? It's not exactly a perfect relationship. Okay? So this area is really a little bit different and might actually have a functional reason for up until generation 4. It turns out between 3 and 4, you actually have a lower cross-sectional area than the trachea. So after that point, that's when you start to see, like you see in all of your blood vessels. Remember we talked about blood vessels, as you increase the generation, the aggregate cross-sectional area of all of the blood vessels at that level was greater than the parent vessel. That happens in the respiratory tract too, except for these initial 3 to 4 generations. The aggregate cross-sectional area there is actually less than the parent vessel. So they think that possibly that has a role in coughing, to be able to have the velocity actually increase up to that point so that when you trigger those irritant receptors, the velocity of the air leaving would actually be faster. Okay, so that's the hypothesis for why you actually see that slight increase. But the normal relationship between these is going to be that as you increase the generation number, the cross-sectional area of all of the airways at that level are going to be higher than the one that branched off into that level. Okay, so if you went from your terminal bronchiole into your alveolar bronchiole, all of your alveolar bronchioles together are going to have a greater area than all of your terminal bronchioles together. Okay? And what happens is, as you increase that cross-sectional area, your velocity is going to go down. Yes?
Do terminal bronchioles have cartilage?
Mm-hmm.
And are they the last generation?
Yes, they're the last generation to have cartilage. And that's actually one of the reasons why you can tend to get collapse of different parts of the more distal airways, is because they lack the structural integrity of that cartilage. As you increase generation number, you reduce the amount of cilia, you reduce the amount of cartilage, and you reduce the amount of mucus. The further into your lungs you get, the less likely you are to have these things, which is also why you are more likely to have an issue where if you don't have equitable distribution of air, it could collapse on itself. That's why your surfactant, which we're going to talk about later, is going to be important. And also why these pores and cones are helping to kind of offset the possibility of atelectasis, which is just lung collapse. That's a great question. Cartilage plays a big role all the way up in your conducting airways, but you don't have that as you move further down into the generations where the alveolar gas exchange is going to occur. Any other questions? Am I losing you? Okay, I can't tell. You have to tell me if I'm losing you. I'm happy to go back, but if you don't tell me, I don't know. Okay, so now we're going to get into lung volume. So we're gonna start talking about a spirometer, we're gonna talk about a couple of different ways to measure these lung volumes. But basically the gist is, when you're looking at a spirometer, you are going to hook up the mouthpiece to your patient, and you're gonna have them take different levels of breath. That air is going to enter into that tube, and you're going to have an inverted canister basically submerged in water. So that when they breathe in and out, that air is either going to be removed or entered into that inverted drum, and it's going to cause the counterbalancing weight to move up or down. That's going to be recorded by a lovely little pen to show you what the relative volume is. Now, one thing you do have to take into account, it's part of the corrective calculations when you're actually doing a spirometer, is that the air that is coming from the lungs is humidified and under the normal temperature inside of your body, whereas the air inside of the spirometer itself is under barometric pressure and is also whatever the temperature is inside that room. So those are corrective measurements. I'm not going to have you do those corrective measurements, okay? Most likely what I'll talk about is I would give you specific lung volumes or lung capacities, or I'll show you a spirometer readout and have you use that to answer a question. Okay, but it is important to know that you do have to make those corrections because temperature inside your body, not the same as the temperature inside the room. Same thing with the humidity. All right. So, this is showing how you would actually hook that up. And as you breathe out, what happens? It's going to cause that counterbalance weight to drop, and you're going to be able to see how that's recorded. When we're looking at a readout, on the y-axis we have our volumes. That is actually in milliliters, and we have our time on the x-axis. So, a typical tidal volume, which is just normal inspiration and expiration, like a quiet, relaxed, normal breathing pattern. Quiet, passive expiration, you're not forcing any air out, you're not forcing any air in, that's your tidal volume. It's usually about half a liter, so about 500 mils for an individual who's about 150 pounds. They also will usually have a roughly 160 mils of dead space. Anatomical dead space is probably about 150. You usually have about 10 mils or so of physiological dead space, or alveolar dead space. So we'll talk about dead space in a little bit. But first, I want to introduce you to all of your lung volumes that are going to be pretty straightforward when you're looking at how to compare your tidal volume, which is TV here. You have ERV, IRV, and RV. These are your four main lung volumes. IRV is your inspiratory reserve volume. That says that it is the amount of air that you can breathe in by force, okay? How can you use your muscles to force as much air into your lungs as you can? Somebody tells you to take a deep breath. The maximum amount of air that you can get in your lungs above your quiet expiration, so that middle peak, is going to include your tidal volume and whatever is your inspiratory reserve. Tidal volume is really just using your diaphragm for the most part. You don't start using any intercostal muscles until you're trying to force air in. ERV is your expiratory reserve. That's where you use your internal costal muscles and internal intercostal muscles and your abdominal and neck muscles to try to force out as much energy as you can. So this would be something that they might do if they were trying to do a test for respiratory conditions, obstructive respiratory conditions. They would have you force out a breath and they would measure what that would come out to. So expiratory reserve says how much air you can force out of your lungs with all of the muscle contractions that you have in your body. RV is your residual volume. That is the amount that never leaves you, okay? What do you notice about the spirometer readout? Do you measure residual volume? You don't. So, because on the y-axis, I tell you there's 1,200 milliliters where the residual volume is, you wouldn't know that. You wouldn't know how much that residual volume was just doing a simple spirometer. The only thing you can measure is the air that's flowing. And since residual volume by definition is air that does not leave your body, doesn't leave your lungs, you can't actually measure that directly from a spirometer. Why do we need residual volume? So your lungs don't collapse, okay? Your lungs will collapse. You have an air-water interface, your lungs are humidified, they need to be. Your cells are still cells, they still need humidity, they still need to be productive when being dried out, okay? So if you didn't have air in there to make sure that those alveolar spaces are still apart from each other, they will stick together and you will have collapsing of your lungs. So that residual volume is necessary. It can be higher or lower based on different pathological conditions that we're going to get into. But the bottom takeaway here is these are your 4 lung volumes. Residual volume is the only one you can't measure from a simple spirometer. So you have to figure out another way to measure your residual volume. Okay? ERV, expiratory reserve. TV is tidal volume. IRV is inspiratory reserve. Okay? You have 4 lung volumes and 4 lung capacities. We'll get to the capacity in just a second. How are we so far?
Are you gonna tell us how to measure the,
Excellent. That's why I wanted to get through this first, and then we're going to do that. Any questions about this?
Okay, so weird question. So you said the inspiration, the IRV, is that like, okay, I take a long breath and then, or is it from like after I exhale, then I completely?
No, so when you have a quiet expiration, which is just your passive, relax your diaphragm, breathe out your normal tidal volume. Once you breathe your normal inspiration, that's your tidal volume. Anything above that is your inspiratory reserve. Okay, so it specifically, the IRV specifically refers to contraction of accessory muscles to bring in extra air that is not part of your normal tidal volume. Your tidal volume plus your IRV makes it 1 year capacity. So that's coming. Same thing with the ERV. ERV specifically is after you've had a quiet expiration, how much more air can you force out if you really try? All right, so here are your capacities. Basically, your capacities are going to be adding 2 or more of your lung volumes. Okay, so we have, these are the definitions that I just mentioned before of your different lung volumes from that same readout that we had before. Your inspiratory capacity is exactly what you just said, starting with your quiet expiration at the base of your tidal volume. Once you take in your tidal volume and whatever your inspiratory reserve is, that is the total capacity of your lungs to take air in from a normal resting value. Okay? This is going to be different than your vital capacity. So your inspiratory capacity looks at specifically how much air can you decide after a quiet expiration can you take in on the next breath. Vital capacity is total amount of air that your lungs can move, period. So force out as much air as you can to get to your residual volume, then inspire from that point on. All of your expiratory reserve, plus your tidal volume, plus your inspiratory reserve is your vital capacity. That by definition is the amount of air that your lungs can move with all of the muscles that you have at your disposal. That value can change based on pathologies, based on injury. What do you think happens to your vital capacity if you just went for a run and then you got a horrible cramp? It's going to be painful, right, to breathe in. Anybody have a cramp after running or exercising, right? You get a really strong pain. The last thing you want to do is take in a really deep breath, okay? If you had anything that caused you to have pain, that could be one of the reasons why you would affect some of these lung volumes, okay? But by definition, your vital capacity is the total amount of air that you can move. The only thing it doesn't include is your residual volume. So all of these that we've done so far, you can measure with a simple spirometer. This is the first one you can't. Your functional residual capacity, by definition, is the amount of air that's left in your lungs after a quiet, passive expiration. Normally, the bottom of your tidal volume is the value that is left That functional residual capacity is what's left after you relax your inspiratory muscle and just let the positive air pressure inside your alveoli allow the air to flow out. Okay, you're not forcing anything out. That's your functional residual capacity, and that's the amount of air that is in your lungs on any given basis. People don't usually force out all the possible air with every single breath. Okay? This is the first one that you can't measure with a simple spirometer because it takes into account what your residual volume is. If I gave you something like this and I asked you, and I didn't give you a y-axis, but I gave you relative amounts, you know, like there were 3 bars between the ERV, there's 1 bar between the TV, you know, and I tell you how much each of those boxes is, you could measure what the change is, the relative change, okay? But you can't necessarily tell me that the residual volume is 1.2 liters, because that's not going to be measured. You can compare, but you can't give an exact value. Your total lung capacity is going, so this is the last one that we were talking about. Your total lung capacity is everything. This is the other one that you can't get from a simple spirometer. So if you wanted to figure out what the various lung volumes and the various lung capacities are, there's one item that you can't get from a simple spirometer, and because of that one item, not only do you not get that residual volume, you don't get functional residual capacity or total lung capacity. So it's still important to know how much residual volume you have, because that's going to be indicative of different kinds of pathologies. So, anybody have any questions on the 4 lung volumes and the 4 lung capacities? Our lung volumes, residual volume, expiratory reserve volume, tidal volume, inspiratory reserve volume. Our capacities, we have our inspiratory capacity, which is IRV plus your tidal volume. You have your vital capacity, which is all of the air that you can move, IRV plus ERV plus tidal volume. You have your functional residual capacity, which is ERV plus your residual volume, and then you have your total lung capacity, which is IRV, TV, so your tidal volume, ERV, and residual volume. So 8 total parameters that we talked about. How are we going to measure that residual volume? The one part I want to point out here that we will get to again when we get into lecture 13, there we go. That FEV1, that is the forced expiratory volume that you can do in 1 second. That's going to play a role when we start talking about our restrictive versus obstructive diseases. How much of your vital capacity, the amount of air that you can move, can you force out, taking in your maximum inspiratory volume, how much of it can you force out in that first second? Should be about 80% of your vital capacity. If you have a problem with airflow, that value will be less. Okay? That was the reason I included this one. But it also labels every single one of them on one figure, so I thought that's nice. This is from the boron book. Okay, so how are we going to measure your lung volume? We have a closed circuit and an open circuit method. Oh good, we still have 20 minutes. Okay, so we might actually get to both of these. All right, so starting with our closed and our open circuit methods, basically there are 2 different ways to get you the information about residual volume. They're going to do it based on a calculation that assumes conservation of mass. All right, so way back to early science classes, conservation of mass is not going to go away, your matter is not going to be created entirely. From that basic principle, in even your closed or open circuit method, the closed and open part specifically refers to the source of the air that you're going to have your patient breathing in and out. It doesn't mean that you're actually losing anything. All of the mass is contained inside of the circuit, which is why whatever you start with can be equivalent to whatever you end with, because the mass is not going to change. We're going to start with our closed circuit method. So this was a figure that I gave you guys ahead of time, mainly so that you could take a look at the setup, and as we're walking through it, you can highlight the parts that are going to be important. So this is a helium dilution technique. It does not mean you're breathing straight helium, okay? That's not the point of this. It's going to give you a set amount of helium that is measurable. And you're going to start at an initial lung volume, so that's your VL. That VL is whatever you decide it's going to be. So as the person running this little test, it's entirely up to you what you want to do. The easiest thing and the most comfortable thing for your patient to do is just to have them do a quiet expiration and start it at your functional residual capacity. You could, in theory, try to force them to have all of the air gone and measure your residual volume directly, but that's not very comfortable, especially when you're getting things set up. So, typically what's done is you have somebody expire, stop breathing, and then you will basically begin this experiment. What you have here is that little yellow thing is basically their airways and their lungs. That's the notion for that in the Warren book. You have the ability, a valve, to open or close the flow of air with this specific spirometer. The parameters that we're going to look at, we have an initial concentration, okay, and we have a volume of air that is inside the spirometer itself and inside the tubing. What happens if you take the concentration and you multiply it by the volume? What do you get? So what is concentration? Units. Mass per. How do you figure out volume? Grams per milliliter, right? Milliliter is the same as centimeters cubed, volume. Okay, mass per volume, multiply it by the volume in the spirometer, what do you get? The total mass that is present at the beginning of helium. So that's what's down here at the bottom. The amount of helium at the beginning is whatever the concentration is that you have added to the air that's inside that spirometer, times whatever the volume is of the air that you've added into that spirometer and that tubing. So that's starting with your helium, that's your mass, okay? There is some set of volume that's in your lungs. That's what you're going to calculate. You're going to calculate VL. You don't know that yet. You know by definition what it is. If it's your FRC, it's your functional residual capacity, but you don't know what the actual volume of that is in milliliters or liters. Once you decide to start this experiment, you open up that little stopcock to allow air to flow, and you have your person breathe. And they just do their normal breathing, which basically dilutes everything out, and you have it go for several breaths until you reach equilibrium between the air that's inside your lungs and the air that's inside the spirometer. So no air should be coming in from the outside, and no air should be lost to the outside. This is a completely closed system. The only flow of air is from your patient's lungs into the spirometer and back. Okay? So we're not going to do this for very long because you don't want them to pass out. And that typically won't happen because it's a very low amount of helium. But you can figure out the initial mass, and since you're not losing any helium, and helium is not going to cross the alveolar wall, it's not something that's going to get into your bloodstream, it's still going to remain, all of it, all that mass of helium is going to remain inside of the system. So when you are done, the concentration of helium inside of your spirometer is going to be lower than it was at the beginning. Why? What did you add to it? What did you add to the helium inside the spirometer and the tubing? Whatever was in your lungs, right? You didn't have any helium in your lungs. So that equilibration results in a lower concentration at the end. But whatever that concentration is, now that you've reached equilibrium, that's the concentration of helium in all of the lung volume. So you already know what VS is. VL is the one that you don't know. So this is what you're going to look for. You are calculating whatever the concentration is, which is going to be lower than it was at the start because you now basically diluted out that helium between the lungs and the air inside the spirometer. So you have to take into account the total volume of air that is in what is now a connected system between the lungs and the spirometer and the tubing. Okay? How are you going to figure out what VL is? oxygen mass. Both of these equations on the left and the right are telling you the amount of helium. The amount of helium hasn't changed. So whatever you calculated as the amount of helium, the mass of the helium on the left, is gonna be the same as the mass of helium on the right. The difference is that you have different concentrations on the left and the right. The right's gonna be more diluted because you have to take into account the lung volume, which was not part of the calculation you got from the initial side. Okay? So if you set these two equal to each other, you can run through the calculation and solve for VL. How do we feel about that so far? Anybody have any questions about this? No? Not at all, huh? So are you guys ready to calculate some of these if I just gave you a quiz? How would you solve for VL?
Plug it on the other one.
Don't forget, you gotta take care of those parentheses as well. So, after you go through and solve for VL, you'd actually end up with this as your equation. Okay? And the main reason for that is because once you multiply that final all the way through, you have the final helium times the spirometer volume plus the final helium times the volume of the lungs, so that when you actually subtract out the HE final times VS onto the other side, and you're left with that divided by the final, you end up with this value here is actually because you have HEF over HEF when you actually follow through on this. So I don't think it's necessary to memorize this equation. That's a little easier to like run through and put a calculation in, because then you don't have to remember what you had and divide. But typically when you're actually given something to calculate, you'll just calculate this and you'll set whatever that value is equal to this here. Yeah?
Is the end of the equation, is that -1?
Yeah, it's a one, sorry. Yeah. All right. So, oh yes.
Are we assuming that the initial spirometer volume is the same as the final spirometer volume?
Yes, because that's not going to change.
Okay.
Because whatever the value is, well, you're not really assuming it's the same. You're measuring that. You can measure that value. But how would you know that it's roughly the same? You're making the decision, right? You're the one running the experiment. So you're deciding at what capacity you want to measure. You're telling your patient, stop breathing at this point in the breathing cycle. And by definition, you're defining what lung volume you're going to calculate. How would you pretty much be a good estimate to get a roughly equivalent end volume of the spirometer after you've had them breathe? Have it. Say it.
Level on the trace, right?
Yeah, keep it at the same point. Say, okay, a quiet expiration is where we're going to start. We'll have a quiet expiration when we finish.
Here's a question.
Yeah.
So earlier you said when using the spirometer, you have to account for temperature and,
You would do a correction here too.
okay.
Yes,
so you
and I
do-
won't have you do that. But that's something that typically is, so that would be factored into like the equipment where they would have, this is what the temperature is. You plug that into like the computer and it would register out what that difference is.
Okay.
Mhm. Yeah. Oh, sorry. So, it's your decision when you start and when you end. If you decide that you want to start at your total lung capacity, that's your prerogative. It's not very comfortable for your patient. Wouldn't recommend it, but you could if you wanted to. If you start at functional residual capacity, how are you going to figure out reserve volume? You're going to get VL here. What's VL going to be if you start at the end of a quiet expiration? It's your functional residual capacity. How do you get reserve volume from that? By definition, what's functional residual capacity? Reserve volume plus
ERV.
ERV. You can figure out ERV from a normal spirometer, right? So you'll have that ERV value, and that you just subtract from whatever your lung volume is. Okay? We good? Okay. Open circuit. So now we're going to look at our open circuit method. This is actually a little bit more straightforward if you're going to do the calculation, because you're not adding up two different types of volumes. Your open circuit, again, is not, it doesn't mean that you're actually going to lose any of the air that you're breathing. And you're not introducing any air from the actual atmosphere. In this case, you actually have a separation in the direction of airflow. So the air that's coming in is coming from one place, and the air that is being breathed out is going into the other spot. So what happens here is you're still going to start with a normal volume of lungs, whatever that lung volume is that you decide to have them stop breathing, that's going to be that initial starting point. And you have an initial concentration of nitrogen. Okay? So you have the amount of nitrogen that is present in your lungs at the start. So mass. What is the mass or the number of moles of nitrogen that you have present in the lungs at the beginning of the experiment? Whatever the concentration is of it in the lungs, times the lung volume you decided as your starting point. How do you know the concentration of nitrogen in the lungs? Yeah, you just measure the air, right? Because they're going to be sitting there waiting for you to come in with all your setup. They're going to be breathing the same air that you're breathing. You can just measure the content of the nitrogen that's inside of the air. Yes.
Wouldn't the concentration change then based on the difference in temperatures between air outside and air in your body?
That's what you would factor in that value to figure out the partial pressure in order to get that concentration. The concentration, the content of the nitrogen that is present in the air can be measured and then corrected for to take into account how much is going to be inside of your lungs. That gives you your initial mass. Okay, we have about 5 minutes. We can get through this in 5 minutes. From this point, when you get ready to start, now you're not breathing in any more nitrogen. The amount of nitrogen that's inside of your lungs is it. That is the total amount that you're starting with. Nothing else is going to be introduced. From this point, you're breathing in 100% oxygen. So every breath coming in is 100% O2, and when you breathe out, all of your expired air is going to go into this balloon for collection. Okay? Basically what happens is, as you're taking air in, it's going to mix with whatever air was inside of your lungs, and you will breathe out. So on your first couple of breaths, you'll notice the pattern of flow for your alveolar gas. It's going to start, right here is your starting point. Okay? That's the starting point of your experiment. As you move through each minute, your patient is still breathing, and every time they're taking in oxygen, they're diluting out this nitrogen and expiring some of that massive nitrogen. The more you breathe in, the less the air that is entering into that balloon is going to have a content of nitrogen. By the time you're past about 7 minutes or so, you've basically expired all of that nitrogen. It is pretty much nil, the amount of nitrogen that's coming out in expired air. So you're washing out the amount of nitrogen inside of the lungs. But because you will still have air in your lungs after you expire, you have to do this for several minutes to make sure that you're basically flooding it with a lot of oxygen to wash out whatever nitrogen is there so that it can get expired into this bag. Once you're at the end of that experiment, you now have all of your nitrogen is present inside of that balloon. So how do you figure out how much there is? Figure out what the volume is in there. And wow. It's not on here. I don't know why I drew it that way. That's weird. Let's try that. Okay. So you're going to start with the volume that's present at the end of your experiment. How much volume of air is inside of that balloon? And what is the concentration of nitrogen inside of that balloon? okay? And that will give you the value that you would have for the amount of nitrogen at hand. Because you're not gaining or losing any nitrogen from the whole system, you can set these two equal to each other. So what's your end result? You have initial times VL is the same as your balloon or your sac, or whatever you want to call it, times that. So you want to figure out what VL is? Divide the right side by the initial concentration.
You have to account for whatever pressure it takes to stretch or expand the air.
You mean for like what the pressure is that's inside there? Yeah, you could measure the pressure inside the partial pressure inside there. And you're talking about the sac. It doesn't typically take, it takes less than 10 minutes to do this. Why might this be preferable? True. What else? Anybody work in a lab? You know how expensive it is to get different tanks with different types of gases? Oxygen's not that expensive. There are a couple different ways that you can do this. It's a little bit easier to have this set up, because basically you just need oxygen tanks, which hospitals are going to have a plenty anyways. So this is something that's relatively easy to set up. But there are two different methods to do it, closed circuit and open circuit, both of which can give you the information about residual volume. You cannot get it from a simple spirometer. You have to do something like this in order to calculate the residual volume left in the lungs. And that's absolutely critical if you're looking at different types of pathologies. Some of them are only going to tell you how much air is going to be moving. If you don't know how much residual volume